In this video, we will overview how to perform integrals on differentiable manifolds. For that, we need to define volume elements with respect to which we will integrate functions, and we will see that such a notion can be defined only on manifolds that are special and have a property called orientability. We will present what partitions of unity are and see how they can be used to define integration on manifolds that have atlases that contain more than one charts. And finally, we will see how integration on manifolds with a metric have a special volume and how we use that one to perform integrations in that case. Let's see what happens in Rn. The first thing that we should understand is that the computation of volumes is a less restrictive structure than having a full metric. A metric computes distances on all possible curves, and that is a more fine structure than being able to compute volumes. And we can see that by realizing that many metrics give the same volumes. Another property that volumes have is that they are linear functions on n vectors, where n is the dimension of Rn. We can see that with an example here, where we are on the plane, the dimension is equal to 2. And the volume in that case is the area of a surface defined by the two vectors w and v. So if we scale the vector w by a factor alpha, then the volume is also scaled by the same factor alpha here. So the same thing happens when we add two vectors. If we have two vectors, v and u, and we consider the area that the vector v plus u spans with w, then this is equal to the area spanned by the vectors v and w plus the area spanned by the vector u and w. In 3 dimensions, we are accustomed to compute volumes by considering the triple product of 3 vectors. We take the cross product of 2 of those, and then we project it on v by using the inner product. And we know that this is equal to the determinant computed by the components of the 3 vectors. And in that case, linearity is trivially seen from the properties of a determinant. So if we take any 2 vectors and in its slot we put a linear combination of 2 or more vectors, then the total volume also is a linear function of each volume separately. Another property that it has is that if any of those 2 vectors are collinear, then the volume that is defined is 0. So the volume collapses to a region that we call it has measure 0. So we want the volume to have the property that if 2 vectors here are the same, then the result is equal to 0. And if we apply this desired property on the vector v plus u, and we do a little algebra that uses the linearity of the volume, we arrive in this expression here. But those 2 terms vanish because they correspond to volumes defined by same vectors, ww and uu. So all that is remain to be non-trivial is the volume defined by the vectors where the 2 slots here have been interchanged, and we have wu and uw. So those 2 volumes must be equal but have the opposite sign so that they will add up to 0. And we realize that such a linear function must be antisymmetric with respect to the exchange of the first 2 slots. But if we repeat that for any pair of slots of this linear function, then we end up realizing that this linear function must be completely antisymmetric to its arguments. And since the arguments are n vectors, then this linear function must be an n form on the manifold. So in Rn, we usually choose the volume element to be defined in Cartesian coordinates. So if we pick a Cartesian coordinate system x1 through xn and consider the coordinate basis dx1 through dxn, their wedge product in this order defines a volume element in Rn. Indeed, this is in agreement with our intuitive definition of volume by considering the action of this form in this particular vector. This is a rectangular parallelepiped where the sides of this rhomboid here, cuboid here, is nothing but multiples of the coordinate basis d1 through d3 scaled by the length of each side, delta x1, delta x2, delta x3. And if you substitute here, then the result will just be the product of the lengths of the sides of this cuboid, which is nothing but its volume. So if delta x1 through dxn, delta xn are taken to be infinitesimal, this is an infinitesimal cell in Rn whose infinitesimal volume delta v is given by the action of omega on those vectors. So if we use this notation, and by x we mean the collection of coordinates x1 through xn, then if we choose a function f of x and multiply it here by omega acting on those n vectors, then the result will be the value of the function times the volume element of that cell. And we know from calculus that if we take delta v to go to 0, and in this process we compute this sum, this is what we call the n-dimensional integral of f of x in region U over n. So since this can be made independent of the choice of the coordinates in a way that we will shortly see, we define the integral of f times omega to be this n-dimensional integral that we know how to compute from calculus. Any other n form in Rn is a multiple of the n form omega by a function f. So the integral of f omega, the way that it has been defined here, is simply the integral of the n form sigma. So actually what we have with integration is not integration of functions, but integration of n forms. We have chosen this special volume element omega to be used in the definition of the integration. But we could have equally chosen omega prime to be our volume element by simply taking a different order in the names of the coordinates. So if, for example, we take a coordinate system that has x2, then x1, then x3, and then xn, then the volume element defined in that coordinate system, omega prime, is equal to minus the form that we used originally. And this is because in the wedge product here, we have to exchange the positions of dx2 and dx1 to obtain omega, and because of the anti-symmetry of the wedge product, we obtain this minus sign. So you see that the overall sign of the integral is just a convention. But what we actually use is to choose omega or omega prime to define the integration and say that after we make this choice, the resulting integral will be positive. And as we will see, this amounts to a choice of orientation in Rn. This ambiguity of sign can be easily seen with these two-dimensional examples here. So if you integrate on a plane or part of it, then there's no natural choice of orientation. It could be up or down, and that is an equivalent choice. Or if you have a slightly curved surface here, what is the inside or the outside of the surface is a matter of taste or a matter of choice. So, as we will see, in order to define integration, we have first to choose an orientation. But after this ambiguity is removed, then everything else is fixed. And for that, we have to make the choice of a positive or negative or right-handed, left-handed orientation and stick with it until we finish our calculations. This is something we implicitly do when we work, let's say, in R3, and we draw a Cartesian coordinate system in this order. We put x, y, and z, and then you see we move in the counterclockwise direction when we look at the axis from this perspective. And that is what we define to be a positive orientation. But this is a matter of choice. We could have equally chosen to put the axis in this way, and then going from x, y, and z, we would be moving in the opposite direction, in the clockwise direction, and that, of course, gives us a different orientation in R3. So we call this the positive orientation, and this the negative orientation, but as we have already mentioned, this is just a matter of taste. So summarizing all that we have said so far, we need a volume element, and that volume element should be an n form, but it should also be nowhere vanishing. And this amounts that when we integrate over it, there will be no change of sign or orientation. So such an n form can be obtained in a particular coordinate system. Let's say now that we don't just pick Cartesian coordinates, but any coordinate system x1 through xn, then any such form can be written as a function h of x times the product of dx1 through dxn, where product now means, of course, with respect to the wedge product, the antisymmetric product of differential forms. The fact that this element is nowhere vanishing, it means that this function here can be chosen to be positive for all x in Rn. Now, if we pick a different coordinate system, x1 prime through xn prime, then, of course, the n form does not change, but let's see how we can express it in terms of the new basis. So the equation that defines omega can also be written equivalently using the Levi-Civita symbol, epsilon mu1 through mu_n. So all the terms here are equivalent up to a sign to dx1 times up to dxn, and by putting here the epsilon symbol here, we make sure that every term here is equal to this. And because we have n factorial such terms, in order to have an equation, we have to divide by n factorial. In the new coordinate system, we can express the coordinate basis dx mu as a linear combination of the coordinate basis in dx mu prime. And this is given by the well-known transformation rule, given by the derivatives of x mu with respect to x mu prime. because of the linearity of the wedge product, all those factors here can be moved in front, and then we have an expression that gives us omega in terms of the new basis. But we recognize those terms here as giving us the determinant of the x mu's with respect to x mu primes. That means the Jacobian of the transformation, and that will be multiplied by a sign given by the Levi-Civita symbols with respect to the new indices mu1 prime through mu prime. These are formulas that we have seen in previous videos. So by getting rid of the Levi-Civita symbols, we realize that now all those terms are equal to dx1 prime through dxn prime. So we have expressed omega in this coordinate system, and you see that the function h of x must be multiplied by the Jacobian j. So if this Jacobian is positive, then we say that the new coordinate system defines an orientation which is the same as the one that x mu defines. But if j is negative, then the two coordinate systems define an opposite orientation. Now we see that the two integrals are the same if the orientation is the same in both coordinate systems. And the reason is the well-known formula from calculus that relates the n-dimensional integral of a function in one coordinate system with the n-dimensional integral of the same function at a different coordinate system, which is the same if we multiply here by the Jacobian of the transformation. So be careful here, j is positive. Therefore, we see why the integral, as it was defined before, is giving us a value which is independent of the choice of coordinates. Let's see this with a simple example and consider the volume of the sphere. In fact, it's volume of the three-dimensional ball, which we will take to have radius r, as I can see here. So the volume element in R3 is dx times dy times dz, and if we change to spherical coordinates, we can express it in terms of dr, d theta, and d phi, but then we will obtain this function h to be non-trivial, will be equal to r squared sine theta, whereas in this coordinate system it's equal to 1. The reason is we have to compute the Jacobian of this transformation, and this is precisely equal to r squared sine theta. So it's a nice exercise to sit down and do those simple calculations that prove this formula. So the integral of this volume form on the ball B3 is the integral of the this expression here in terms of the spherical coordinates. But according to the definition that we have given to integrals, this is just the three-dimensional integral of r squared sin theta dr d theta d phi. Now, let's discuss a little bit the details. Although elementary, we have to see some fine points in the calculation. So, when we compute this integral in calculus, we choose the order of performing the integrals to be the one that is more convenient for us. And then we have Fubini's theorem that states that the integral will be independent of this choice. But as long as the limits of integration here are chosen so that they map to the region of integration, which in our case is B3. So here we can choose, for example, to perform the phi integration first, we integrate phi from 0 to 2 pi. Then the result is integrated over theta. Theta is integrated from 0 to pi. And then the final result is integrated over r. Has to be multiplied here by r squared to give us the final answer. And notice here that the order of the integration limits cannot be arbitrary. We should integrate phi from 0 to 2 pi and not from 2 pi to 0, which would have changed the sign of the integral. And similarly for the theta, we can integrate from 0 to pi, but not from pi to 0. Now the reason is because when we define integrals in Rn, by their definition, the volume element is positive. We define the integral as the function times a positive volume, delta v, and then we take delta v to 0. But delta v in this process is always positive. So such volumes should come out to be positive by definition. So now the integrals can be performed. The inner integral gives us 2 pi. The theta integral gives us a 2 times 2 pi, that's 4 pi. And then the integral over r will give us r cubed over 3. And we end up with the familiar formula of the volume of the ball, which is 4/3 pi r cubed. And notice that we have obtained the correct sign, which is a plus. Now, let's make a change of coordinates. A simple one, but it will make us understand better the concept of orientation. So, instead of using r, theta, and phi, let's use the coordinate system which is r, phi, theta. So, our coordinates x1, x2, x3 are r, theta, phi, and x1 prime, x2 prime, x3 prime are r, phi, theta. Now the Jacobian is non-trivial because we obtain those two off-diagonal elements that will give us an overall minus sign when we compute the determinant. So actually this Jacobian here is negative, indicating that now the orientation has changed. Now we have defined integration with respect to omega by making it the volume element in R3 or in B3, whichever you like. That is an integral of r squared sin theta dr d theta d phi. Now we change coordinates, and in the new coordinates the function h does not change, it's the same. And now to compute the integral in the new coordinates we have to include the Jacobian here. So that will give us a minus sign times the function h of x, r squared sin theta. But now you see that the form is dr d phi d theta. So we can compute the integral with respect to omega by making a swap here between phi and theta, but that will introduce a minus sign. And this minus sign will cancel exactly the minus sign coming from the Jacobian. So we will end up with the same result, plus 4/3 pi r cubed, which is the volume of the ball. The volume is positive in any coordinate system. There's nothing special by choosing a coordinate system. So we could have defined omega prime to be the volume form in R3. That's perfectly fine. All we do is just change the order of theta and phi, and we obtain this form omega prime here, which of course has the opposite sign from our previous choice. So omega prime is minus omega. So now we will perform integrations, but we will use the opposite orientation. Now, since this is what defines integration on the ball, then the integral is r squared sin theta dr d phi d theta with this order. And that, by definition, is the three-dimensional integral r squared sin theta dr d theta d phi, which gives us the same result as before, a positive result. But now, if we integrate omega, which is minus omega prime, the result will be different. It would be minus 4/3 pi r cubed. So you see that the integral of our form changes sign if we change the orientation. But the overall change of orientation can be anything we like. We can choose omega to define an orientation, or omega prime to define an orientation in R3. So we need to have a volume element, and as we will explain very soon, this can be given by any nowhere vanishing n form. For this to be possible, the manifold must have a special property, which is orientability, that not all manifolds have. Let's see what this is. Let's consider a manifold and two charts that have a non-trivial overlap, u and u prime, and their intersection here is a non-empty set. Let x mu and x mu prime be the coordinates in those two charts, and they are such that on the intersection of the two sets u and u prime, the Jacobian is positive. We will say that those two charts define the same orientation on the manifold. Now, whether this is positive or negative, this is a convention. We use the same language when we refer to the bases defined by the coordinate systems. So, if we have a coordinate basis in the tangent space or in the cotangent space, then the basis in the two different coordinate systems, we say that they have the same orientation. So, if this is possible to be extended over the whole manifold, that means if we can find an atlas that covers all M, such that at the intersections of those charts we have the same orientation, then M is orientable. But this is a definition, and there is no guarantee that a differential manifold will have this property. So, if we have an orientable manifold, though, then there is a nowhere vanishing n form omega, and that can be chosen to be the volume element. And we know that there are an infinite number of those, so the choice of volume element is something that depends on our taste. And we can see that because any two forms are related to each other by just multiplying one by a function on the manifold M. If, however, this function is positive everywhere, that means non-vanishing too, then omega prime and omega are called equivalent with respect to the orientation. If this function is everywhere negative, then this gives the opposite orientation, but both n forms can be equally chosen to be volume elements for the manifold M. Now, if H is vanishing somewhere, this will make omega prime not a good choice for a volume element. First, because the volume will not be well defined at that point, it will be a singular point, but this is also an indication of a change of sign for this function. So forms where with respect to a volume element can be expressed with functions that don't keep the sign over the whole manifold are not good volume elements for the manifold. So let's make this more explicit with an example. Let's define such a volume element. The first thing is we pick a smooth function on the manifold which is everywhere positive. for every point P. Now we choose a coordinate system and we restrict our attention to it. We define the n-form on this chart to be the function h, which I should stress is defined over the whole manifold, times the wedge product of dx1 through dxn by using the coordinates of this chart. We can equivalently write the form here in terms of the Levi-Civita symbol, which will also allow us to write down what the components of this form is, which is just the Levi-Civita symbol times the function h. So the function h is related to the unique independent component that an n-form has on UI. Now we can extend this definition of this form over the whole manifold by first considering its extension to a neighboring chart. So if we have a chart U prime that has a non-trivial overlap with U, and it has the same orientation with respect to U, that means the Jacobian here is positive, then we extend omega to have to be the n-form defined on the union of U and U prime now, that is given by this expression. Now, on the intersection of the two sets here, the definition is consistent, because in any whether you use this one or that one, you will obtain the same form on the intersection. To make the extension over the whole U prime, we make an analytic continuation of the Jacobian over the whole set U prime. So we repeat this with charts that cover the whole manifold. Then by construction, this n-form is indeed an n-form whose components are transformed as components of n-forms should transform. So you see, if we consider the components in a different coordinate system at the intersection of two charts, then these are indeed related by this relation, because if we substitute here the definition of the form here, epsilon times h, then we will obtain the Jacobian times hx prime, which is the definition of the components on the different coordinate system. So this is true for any pair of charts that have a non-trivial intersection, and that will give us an n-form. Let's see a very simple example that orientability is not a property of all manifolds, and consider the familiar case of the Möbius strip. So how do we obtain the Möbius strip? We can consider a strip on the plane. This can be extended infinitely if you want, or if you want you can restrict it to finite values. But the important thing is that those line segments here are identified in the opposite direction. Of course, this cannot be seen on the plane. You have to go to a hard dimensional space and see how the gluing of those two sides must be done. And here you see a nice picture of such a strip, Möbius strip. Now let's consider an atlas on the Möbius strip. The atlas U01 is defined here by the blue set. It starts from those points here. It's an open set, of course, it doesn't contain the line, but all the points contained here. Then we move here. Now this line here is identified with this, so we continue here. So U1 is this set, and be careful, this is not a disconnected set. This is a connected set because of the identification of the two lines. And you can see that in 3 dimensions explicitly by noticing that U1 starts from here and then ends somewhere there. So this is a region of the Möbius strip which is connected. Now, the other chart of the atlas is the set U2. It has non-trivial intersections with U1 here. Then it extends and meets the other side of U1, and we also have a non-trivial intersection of the charts shown here on the right-hand side. So if you look at it in the Möbius strip in R3, then the set U2 starts here. There is an overlap of the two sets. We go around, there is an overlap there, and then it ends here. So that consists of a chart on the Möbius strip. So a coordinate basis can be defined on its chart. Here we have chosen coordinates that are Cartesian-like. So if we are on U1 here, you can use x and y coordinates. Well, you can put the origin anywhere you like here, and you start from a minimum value of x and end up with a maximum value of x there. Similarly for y, minimum y and maximum y. So that will define a coordinate basis E1 and E2 that point in the direction of the increase of each coordinate. So we will get this coordinate basis, which are vector fields defined on all points of U2, and here we see 3 instances of those vector fields. Now you can try and do the same thing on U1, but now you have to be careful. Indeed, we can choose the x-coordinate here to move in the horizontal direction. You can put the origin of the x-axis anywhere you like, let's say here. It will start from a minimum value, then reach this point. This is identified by that point, so you will continue in this direction, and here will be the maximum value of the coordinate x. Now, in the y direction, then you put the axis here to point upwards. You go from a minimum value to a maximum value, but then as you move along, at this point you have to reverse the axis in this representation. So here the y-axis points upwards, but with this choice on the left-hand side here it points downwards. So if you build the coordinate basis, E1 points in the direction of increase of x. It goes always to the right. Here it goes to the right, and here it goes to the right. But E2 must point in the direction of increase of y. So it goes in this direction here, but now the y-axis is reversed. So E2 points downwards. So if you want to draw those vector fields on this strip, you have to reverse E2 every time you move from a right region to a left region. And that can be seen here in unambiguously in 3 dimensions. So you see E1 and E2, then you go around, and as you move along, this vector here is flipped in its direction, and it's pointing in the opposite direction as it is moved closer to this one. So as you can see, the orientation between the 2 coordinate system is consistent on the intersection on the right hand side, but it is inconsistent on the left hand side. So if you take the basis here defined on U2 and you move it around, then at any point on the left here it has vectors pointing in this direction and that direction. But if you take the basis on U1, then you see as you move it continuously here, then you come up with the E2 vector pointing in the other direction. So you see this basis here and that basis there cannot be identified because E2 points in the opposite direction. So this is why the Möbius strip is not an orientable manifold. So let's see how to define integration on a differentiable manifold. We will start by defining integration on a chart and then extend this definition to an atlas. Let h be a positive function on the manifold and define the form given by this function and the wedge product of the coordinate bases. We define the integral of f times then form omega to be given by the ordinary integral of the function f of x times h of x on the region of Rn defined by the image of ui in Rn. A little bit about notation here. X here is a notation for the collection of all the coordinates x1 through xn. The function f of x is of course the composition of the chart map chi with f. H of x is the same, it's the composition of chi with h. And of course we remember that the point x on this set is mapped by the inverse function to some point here on the manifold. Now let's stress again that the integral on the right hand side is an ordinary integral on Rn, an n-dimensional integral that we have learned how to compute in calculus. And it is defined by considering a positive volume element in Rn. Let's see how we can extend this definition when we have two charts defined on regions ui and uj of the manifold, such that their intersection is non-trivial. Using the definition on a separate chart, the integral on ui is given by this ordinary n-dimensional integral, and the integral on uj is given by the integral of the form omega as it has been analytically extended over all the region uj before. So for that we use the Jacobian of the transformation between the two coordinates on the intersection of the two sets, and then extend the definition of j analytically over the whole uj. So you see that this definition is consistent with these formulas here are consistent with the definition of the manifold omega over the union of the two sets ui and uj. So this definition is consistent because the integral on the intersection of two manifolds, where we can compute it by any of those two formulas, the result is the same. So if we use the definition of the integral on ui, the integral is given by this formula here, and if we use the definition of the integral over uj, then the integral on the intersection is given by that formula. But we know from ordinary calculus that the result of this integral and the result of that integral is identical. So if we want to say what is the integral of f times omega over the union of the sets, we can, for example, use compute the integral over the union over the set ui plus the integral of f omega on the complement of the intersection with respect to uj. So that is a nice definition for the integral, and it is correct, but it is not very convenient when the structure of the union of more than two charts is more complicated. So let's look at an equivalent definition of this integral over the union, but that it will be easier to use when we extend the integral over the whole manifold. So let's pick two functions, epsilon I and epsilon j, which are defined on the whole manifold, not just on the charts, but the index I here connects this function to the chart ui and this function to the chart uj. So this will be made clear in the definition here. First of all, the two functions must be non-negative. So they can be 0, but they cannot take negative values. The function epsilon I is connected with the chart ui in the sense that the support of the function is restricted to ui. So for any point that is not in the set ui, this function epsilon I is equal to 0. Similarly, for epsilon j, the support of that function is the set uj. So for all points that do not belong to that set, this function must be equal to 0. But at the intersection of the two sets, ui and uj, the functions can take any value they want as long as it is non-negative and it adds up to 1. Of course, this requirement makes also the functions ei and ej to take values that are less or equal to 1. So let's look at the situation here pictorially. This is ui here. So at the complement of the intersection with respect to ui, epsilon I is 1 and epsilon j is 0, because the support of epsilon j is in the set uj. And you see that epsilon I plus epsilon j is trivially equal to 1. Similarly, in the complement of the intersection with respect to uj, epsilon I is 0 and epsilon j is 1. Again, the two functions sum up to 1. At the intersection here, ui intersects uj, the two functions take non-trivial values, but they have to add up to 1 for each point in the intersection. Then we define the integral of f times omega on the union to be the integral of epsilon I f omega plus epsilon j f omega, but the integration is done on the regions ui and uj respectively. Now, first of all, you see that these are integrals that can be computed on each chart separately, and we have already defined how to do that. But you also see that if we add up the integrals here, then we obtain f omega if we require the integral to be linear with respect to union of regions of integration. So if we take the union of ui and uj and split it in the complement of the intersection with respect to ui, the complement of intersection with respect to uj, and the intersection, then you see here that each term here has epsilon I plus epsilon j equal to 1. So this is simply the integral of f times omega on these regions, which when we take the union of those regions, that will give us the integral of f times omega in the union, over the union. Now, the reason why this definition is useful is because each integral here, each term, can be separately computed on the different sets ui and uj. So the first term here is given by the n-dimensional integral of epsilon I times f times h. We know how to compute that. Then the second term here, which is epsilon j times f omega, will be computed using this formula, which is epsilon j on x prime, f of x prime, h of x prime, times the Jacobian of the transformation and its analytic continuation over the whole set uj. So we give the definition of this integral to be the sum of those terms. Now we use the notation that the function fi is f multiplied by epsilon I and fj to be f multiplied by epsilon j. You see where I'm getting at in the case where the intersection of charts has a complicated structure. Here we will assume that M has an additional topological property, which is paracompactness, which means that every point P that is covered by a union of open sets can be also covered by a finite number of those. So if M is paracompact, there exists an atlas where every point P is covered by a finite number of charts. It can be a large number, but it's not infinite. So we see here an example where the point P has a neighborhood that is covered by all charts U1 through U4. So we have to extend these definitions of functions of epsilon 1 through epsilon 2, in the case of two sets, to functions epsilon 1, epsilon 2, epsilon 3, and epsilon 4 in this case, but in the general case, the number of charts here is immaterial, so we will consider a chart that has, at the neighborhood of each point, has a finite number of intersections. So if we have such a chart, the numbers of sets here can be infinite, we define a partition of unity subordinate to the chart to be a family of differentiable functions on the whole manifold, epsilon I for every point P. Now, these functions have to have the same properties we had for the two sets, Ui and Uj, but generalized now to any number of charts. So all those functions here must be nowhere negative. The support of each function is non-trivial only on the respective chart Ui. So epsilon I can have non-zero values only for points P in the set Ui. For every point P, if you consider the set of functions epsilon I defined at that point should add up to 1. Now, this sum is infinite, maybe, but the number of non-zero terms in this sum is always finite by assuming that M is paracompact. Then a function f at a point P can be trivially written as the sum of epsilon I, which is 1 times the function, but now we use the notation of fi to denote the function f multiplied by epsilon I. And then we can define the integral of f omega over the whole manifold M to be the sum of those integrals that are done each one separately on each member of the chart. So we take each chart separately, we pick up the corresponding member of the family of the partitions of unity, multiply the function f and obtain fi, and then we compute this integral by doing an ordinary n-dimensional integral in Rn. At the end, we have to sum up all those values to take what is called the integral of f omega on the manifold M. Let's see this with a simple example. Let's consider the circle. And you know that the circle cannot be covered by a single coordinate chart. We have to use at least two. So we show here two charts, U1 and U2. U1 takes all the points of the circle except the point E in the east direction and maps it in the integral from 0 to 2 pi. And then U2 takes the whole circle except the point W, which lies in the west, and maps it to values of theta between minus pi and pi. So this map is given by functional form that is the same, but they're not the same functions because they have a different range. So theta is mapped to the point P on the circle given by Cartesian coordinates cosine theta, sine theta. So let's make sense of an integral over the circle. First, we have to pick up a volume form, which is taken to be d theta. Of course, you see that this defines an orientation because the positive orientation is going around the circle in this direction and not in that direction. And let's choose as the function f of theta to be integrated with respect to that volume element to be cosine squared theta. So this is a function defined over the whole manifold. To compute the integral, we have to compute the integrals over the separate charts U1 and U2, and for that we need to define a partition of unity. So let's choose the members of that family of functions to be epsilon1, defined that is related to the chart U1, to be sine squared theta, which originally takes values between 0 and 2 pi, 0 and 2 pi not included. Of course, that defines epsilon1 to theta everywhere but at the point E. Similarly, epsilon2 is defined by cosine squared theta, where theta is now ranging from minus pi to pi, and that defines epsilon2 everywhere but at the point W. So these functions are extended over the full circle by defining the value of epsilon1 at the point E to be 0. This is a point which is not in the chart, therefore this value has to be 0. And that is compatible with the value that epsilon2 has at the point E, which is equal to 1. So epsilon1 and epsilon2 at the point E add up to 1. Similarly, visiting the point W here, now W is not included in the charts U2. Therefore, epsilon2 on W must be equal to 0. That is compatible with the value that epsilon1 takes at the point W, which is equal to 1 according to its definition. Therefore, epsilon1 plus epsilon2 is 1 for all the points on the circle, including the east and west point. Using the definition of the integral, we have to compute the integrals epsilon1 f omega and epsilon2 f omega over the regions U1 and U2. Our function is equal to cosine squared theta. Epsilon1 is sine squared theta times f. So this gives us the integral sine squared theta cosine squared d theta, which is an ordinary one-dimensional integral where theta ranges over the range of the chart U1, which is from 0 to 2 pi. Now the other integral here uses epsilon2 from the partition of unity, which is cosine squared theta over 2, times the function cosine squared theta. And now when the integral is computed in R1, theta ranges from minus pi to pi. And these integrals you know very well how to perform. Each one is equal to pi over 2, so the final result is equal to pi. And you can see that the same is true if you compute the integral of cosine squared d theta from 0 to 2 pi as you do in ordinary calculus. So now let's focus a little bit on manifolds that have a metric. We have said in a previous video that when a manifold M has a metric chosen on it, then there is a special n form which is the Levi-Civita tensor. And the Levi-Civita tensor is defined by this formula here on a chosen coordinate system x1 through xn. And this definition, of course, is independent of the choice of coordinate systems, and for each coordinate system we can have the same expression where the determinant here and the n form here are expressed with respect to the chosen coordinate system. Notice here that all the terms here are equal up to a sign, and if you multiply this with the Levi-Civita symbol, you obtain dx0 through dx minus 1. So there's only one term actually in this sum, and all those terms are equal. That's why this 1 over n factorial comes here to take care of. Now we choose the Levi-Civita tensor to be our volume element, and this is a natural choice. And we can see that by diagonalizing the metric. So we choose now a basis in the manifold. This will not necessarily be a coordinate basis, but let's write it this way. It doesn't matter for this purpose of explaining this point. So when the metric is diagonalized, then its determinant is simply the product of its eigenvalues. And if the metric is expressed in the coordinate system of the eigenvectors, this is a diagonal metric where the diagonal terms are the eigenvalues of the metric. So the determinant is simply the product of those diagonal elements. But each term here is the product, is the value of the metric on each member of the basis separately. And this is nothing but the inner product of a vector with itself, by definition. So you see that square root of g is the absolute value here of the product of the inner products, the square root of the inner products of each member of the basis, which we can call the norm of those vectors. So there is an absolute value here. Sorry, I forgot it. So by making this observation, let's now consider the value of the Levi-Civita tensor on a set of vectors which is defined by the coordinate basis d0 through dxn1, but now multiplied by scalars, real numbers, delta x0 through dxn minus 1. So if the metric is diagonalized, this is this product here, which will give us a volume that is defined by a rectangular cuboid that has sides the vectors d0, d1 through dn1, but their sides have lengths which are given by delta x0, delta x1, and delta xn minus 1. So this gives us a volume element that is the natural volume element given by the way we have chosen to measure lengths in a manifold. So all integrals are defined with respect to the Levi-Civita tensor as a volume element. So we can integrate functions f or forms omega, which are f times epsilon, by computing the integrals the way we have defined them for any volume and form before, for this particular, of course, and form. Now, in the physics literature, many times we write the integrals this way. So an integral of a function f with respect to the volume element given by the Levi-Civita tensor is written in a similar way that we write n-dimensional integrals in Rn, but what we actually mean is that this is an integral of an n form, which is given by dx0 times dxn minus 1, the determinant, the square root of the determinant of the metric, times the function. So, but this is a convenient and fast way to write down formulas in physics, but we should always remember that what is actually hidden under the hood for the computation of this integral.